Welcome to The Explainer. Today, we're jumping into a philosophical duel from 300 years ago that started with a really simple question, but ended up, well, totally redefining how we see reality itself, all the way down to the quantum level. So let's start right there with that question. Could two things be exactly alike? And I don't mean just, similar, like two iPhones off an assembly line. I'm talking truly, fundamentally, indiscernibly identical in every single conceivable property. Could two things like that even exist? Well, that simple puzzle kicked off one of the greatest intellectual battles in history. So this whole thing played out in a series of letters between two absolute heavyweights of the time. In one corner, you've got the German philosopher and all-around genius Gottfried Wilhelm Leibniz. And in the other corner, the English theologian Samuel Clarke, who was a close friend and basically the public defender for Isaac Newton. Okay, so to really get where Leibniz is coming from, you have to understand that he saw the universe as this perfectly logical, perfectly rational system. And for him, that whole vision was built on two incredibly powerful principles. First up is this big one, the principle of sufficient reason. It's the idea that reality isn't just random or arbitrary. For anything that exists, for anything that happens, there has to be a good enough reason why it is the way it is and not some other way. For Leibniz, this meant the universe was fundamentally understandable. Now, that first idea leads him straight to his second, much more controversial principle. And this, my friends, is where the real fireworks begin. It's called the Identity of Indiscernibles. And what it says is if you have two objects that share every single one of their properties, then they can't actually be two different objects. They have to be the exact same thing. So you take those two ideas, you put them together, and you get Leibniz's pretty stunning conclusion. In a perfectly rational universe, there would be no reason for God or for nature to create two things that are exactly the same. It would be illogical, a waste of effort. Therefore, every single thing in the universe has to be absolutely unique. No true duplicates allowed. But on the other side of this debate, Samuel Clarke just wasn't having any of it. Representing a more down-to-earth, common-sense view, he fired back with a simple but really powerful objection to Leibniz's whole grand system. Clarke is basically just saying, whoa, hold on a minute. His point is brilliant in its simplicity. Even if two things were perfect copies, identical in every quality you could measure, the very fact that we can point and say this one and that one means they are two different things. Sharing properties doesn't just magically merge them into one. And this, right here, boils the whole conflict down to its absolute essence. For Leibniz, if all the properties match, X is Y. It's an identity. For Clarke, you can have all the properties match, and they're still just X and Y, two separate things. It's a huge clash between a beautiful abstract principle and our gut feeling about how reality works. Clarke really drove his point home with a thought experiment. He said, okay, just imagine two particles. They are perfect mirror images, identical in every way you can think of. The only difference is that one is right here and the other is way over there. I mean, isn't their location in space a property? Doesn't that make them different? For Clarke, the answer was obvious. For Leibniz, it was a deep challenge to the rational structure of the universe itself. So the big question is, after all that back and forth, who won? Well, back in their day, the answer was pretty much nobody. The whole thing ended in a draw. The letters they wrote back and forth got pretty intense. They started talking about God and free will and all sorts of huge topics. But in the end, it just kind of fizzled out. There was no knockout punch. Neither side could definitively prove the other wrong, and the question of whether two identical things could exist just hung in the air. But hold on, because the story absolutely does not end in the 18th century. In fact, this is where it gets really fascinating. Because even though the debate itself was a stalemate, the ideas it brought up had this massive, lasting echo, one that would end up shaping fields of science and logic that Leibniz and Clarke couldn't have even dreamed of. And it's this statement from Clarke that maybe without him even realizing it, completely changed the game. By putting it like this, he shifted the whole focus. It wasn't just about objects out there in the world anymore. It became about the language we use, the names we give things. The problem went from being about metaphysics to being about logic. And that one little pivot from things to words, man, it had huge ripples. It forced thinkers to really nail down what identity even means, which helped give birth to modern mathematical logic. It changed how we think about language. But its most shocking echo was in a field that didn't even exist yet, quantum physics. Okay, so get ready for the big, mind-bending plot twist. Centuries later, we invent quantum mechanics, and we discover that at the tiniest subatomic level, particles like electrons can be, well, truly identical. You literally cannot tell one electron from another. They are perfect, indistinguishable duplicates, the very thing Leibniz said was impossible. And that leaves us with this final, really provocative thought. It seems like quantum physics proves Leibniz wrong and Clarke right. You can have two identical things. But here's the kicker. Clarke argued from common sense, from the idea that one thing is here and another is there. But the quantum world breaks all those rules. So was Clarke right, but for completely the wrong reasons? Did a 300-year-old philosophical debate find its weird, unpredictable answer in the strangest corner of modern science? It just goes to show you how these abstract ideas can completely change the way we see reality itself.